Hello. In this lesson, I hope to teach you guys a little bit about light and some of its properties. Light is obviously a really important ingredient for growing crops. So the better we understand light, the better we can understand what plants need and how best to supply it. Before I get started, this is a picture of a pretty cool greenhouse in Australia. In the PowerPoint version of this, that link is active. Sundrop Farms, you can Google it up. What we have here is an array of mirrors. All these mirrors are on tilting computer controlled angles that will focus the sun as it arcs across the sky. All the light that comes in gets bounced to this pole, regardless of where it comes from. It gets bounced to this pole. And they take seawater in the pole and they turn it to steam. And the steam is then driven down through turbines to make electricity. And the condensation is collected as irrigation water. So they're using ocean water to grow their crops. Not to mention, one of the elements that's in abundance in the ocean is potassium that is also made available to the crops. The electricity that is generated is enough to run the entire farm, and they grow hydroponic strawberries, peppers, and cucumbers in this farm. We had a graduate that was a grower there for a number of years, and he switched to selling seeds for an international company, so he's not there anymore. But this is a pretty cool greenhouse in the middle of the desert, producing amazing fruit. So um, anyways, about light, let's talk about it. Uh, Defining it, then we're going to talk about the different energies in it and how it interacts with objects, and then what plants need, and then eventually how we measure it. But I think what we'll see is this last part I've split off into next week's lesson. So, all right, let's define it. This section might get a little geeky physics on you, but just bear with me, okay? Um, Basically, light is two things. It's a wave and it's a particle. Let's start with the wave part of it. Um, as you deal with the different colors, like red all the way down to blue, you'll notice that the wavelength changes. So long wavelengths tend to be red colors, and short waves tend to be blue. So UV is down here, it's even shorter. I'm really horrible at drawing with a mouse. Okay, so keep that in mind, right? The wave properties of light. Red spectrum, longer wavelengths, blue to UV, shorter wavelengths. Um, this is a, the physicist Schrodinger was the one that sort of helped elucidate that light is both a wave and a particle. Obviously, this seems kind of a hard thing to conceptualize, but it is. This is a classic experiment you can do yourself at home if you really want to try some home physics. You take a like a recipe card and cut two narrow slots about maybe 1.5 centimeters apart. Get a really bright flashlight and shine it through both those slots against the wall, and you will see on the wall multiple white lines, because what's happening is the light goes through the slots, it refracts, and you end up with a white line here and there and there and there and there and there all the way along the wall, because it's sort of replicating like a wave as it bends through that slot and warps out in the different directions, projecting this image of a slot on multiple spots on the wall. So that was one of the earliest experiments done to prove that light was like a wave. This is what that card would look like, and this is kind of what you would hope to see on the wall. If you have a bright flashlight, you can do this. Just, you don't have to, but if you want to, why not? It's kind of cool. As far as light being a particle, that's something we actually rely on for solar panels. Think of it as light coming in, colliding with the silicon molecules in the solar panel, and that collision, because a particle kind of has some mass, that collision actually knocks electrons off. And that's where we get electricity flowing through the panel into our homes, making fairly low cost electricity. How does that relate to the energy and whatnot? Well, here's the deal. We need to understand different energies based on what they present to plants and how they can absorb and what's dangerous and what's not. And blue lights, the short, high energy wavelengths, can do some damage, especially UV, right? I think we all know that. Seems fairly obvious. Long wavelengths will just generally warm us, but they're not going to damage us. In the case of UV, the energy is so intense that as it hits our body, it actually damages our cells, breaks the DNA, and those cells end up angry, and the immune system shows up trying to fix it or kill the cell so it doesn't become cancerous. And so blue spectrums are fairly powerful. So if you look at a lot of grow lights, you'll notice that they have a lot of red elements and not a lot of blue elements. And that's partly because the blue produces a lot of energy just by the fact that it's a blue spectrum, that shorter, more intense wavelength. So that's why there's fewer blue elements in a grow light than red in that sense. It has also to do with absorption and what the plants can use, but ultimately, from an energy perspective, they're not that far behind because blue is so much more energetic. Looking at the light coming from the sun, it actually, obviously the sun produces light in all sorts of wavelengths. And in the middle here is what's visible, right? All the way from X-rays, UV, infrared, microwave, FM and AM radio and long wavelengths, all these sort of spikes that come off the sun. And then there's this visible spectrum in the middle that we can see. Very little component of the whole thing. So, summarize here. Light comes in different wavelengths, okay? Obviously different colors, and different energies per photon, or what we call quantum. And red, being the longest, is the least energetic, and violet, or blue, is the most energetic in the visible spectrum. So how does it interact with objects? What does that mean for us in the greenhouse context? Obviously, light, especially the red wavelengths, will absorb to surfaces and warm them gently. And in the case here, we have an incandescent bulb, which produces a lot more infrared heat and also consumes more electricity. It's melting the chocolate, as you can see here. Where the LED light, which is a lower wattage for a similar light output, although to be truthful, not entirely the same amount, is actually not melting the chocolate because it doesn't have the infrared element in the spectrum. So how energy in a wavelength, what wavelength it is definitely a consideration, but also how well a surface absorbs it is important. And that's when we talk about something called the albedo effect. I think instinctively you all know this is true. Like in the winter, sunlight reflects off the snow because it has a high albedo or reflectivity, whereas sunlight does not reflect well off a black surface because a lot of the light is absorbed. So in this case, up to 80% is reflected. That's how you can get a sunburn in the winter. And for a dark surface, very little is reflected. A lot of it is absorbed. So this is when you have energy absorbed, obviously it becomes energetic. It absorbs that energy, so it's going to get hot, just like the brown chocolate melted in the previous slide. So when we talk about albedo, that has to do with the reflectivity of the surface. When it comes to greenhouses, we rely on this when we spray greenhouses with whitewash. So the person here is walking along spraying the greenhouse with whitewash, which is a kind of a lime mixture, often a latex mixture with paint that will then reflect sunlight. So then when you have 100% of really bright summer sun coming, 80% is reflected, which means 20% goes in the greenhouse. But there's so much coming in, we don't need it all, and we don't want the heat. So whitewashing is a very powerful tool for maintaining a suitable climate in the hotter months of the year. we'll talk a little bit more about that in another course at another time. As far as the albedo effect, there's a really interesting global climate impact of greenhouses. This is a bonkers place. This is called Almeria, Spain. On the top corner here, you're looking at how many greenhouses and the kind of density that they exist there. This is a satellite image of this part of Spain. It's all greenhouses, everything. It's insane. Almeria, Spain supplies a lot of the vegetables to Europe, all grown in greenhouses. And what's interesting is that if you look at it, even from space, you can see that a lot of light reflects off the greenhouses. And in fact, because of the albedo effect, it's actually a couple of degrees cooler in Almeria than other parts of Spain, which helps make the climate even more suitable for greenhouses. It's cool and a bit disturbing all at the same time. I'll tell you that Almeria, Spain is not without its controversy. In about 10 years ago, this place was real dumpy, and they had a lot of sketchy illegal labor that wasn't treated well. But with the EU forming out of Europe and the strict rules that all the EU members have to conform to with their labor laws and stuff, it has actually really improved Almeria. And this is an older photo, but they have a lot more modern greenhouses, and the employees are treated a lot better. So that's a happy news story. I would say it still has some room to go, but you know. And then again, talking about wavelengths and surfaces absorbing. Okay, this is where things get important, right? So let's say we've got the sun shining, and it shines into the greenhouse, shorter and longer wavelengths. That sunlight heats greenhouse surfaces, the floor, right? The plants, heats the plants, maybe the benches. And those surfaces in turn get warm, and when something's warm, it radiates heat. Because of physics and thermodynamics and stuff, I don't want to scare you all with that, but essentially, no system is perfectly efficient. So when light comes in and hits a surface, right, some of the light is reflected immediately, and some of it is re-radiated, but at a longer wavelength and slightly less energy. And so some of the wavelengths are long enough that they can escape the glass as lost heat, and some are long enough that they can't actually get to the glass and they bounce off it. They're trapped. So the long infrared warm wavelengths are trapped. This is what we call the greenhouse effect. It's a bit of a sore spot for me because that, over here has become sort of the term for climate change, right? So sunlight enters the Earth's atmosphere, heats the Earth's atmosphere, it re-radiates. Some of it escapes to space, but the longer wavelengths are trapped and bounce back, and the climate becomes warmer. I think last class I talked about how molecules in the atmosphere also heat up, and they re-radiate energy at a lower energy, which then gets trapped. That's the greenhouse effect. That's how that works. And to be honest, with greenhouses, we rely on that because that's how we get free heat in the winter. Anytime the sun is shining, there's lots of warmth. I know from my experience with our greenhouse, in the middle of January, it could be -10 outside, and if the sun is shining, I don't need my boilers. The place stays plenty warm. There's many days in the winter where you're actually opening your vents to cool off the greenhouse because it can get quite hot. So the greenhouse effect is important. So this idea of light that's transmitted through the glass heats the surface. That surface gets warm, re-radiates on a wavelength that gets trapped and bounced back into the greenhouse. So the whole greenhouse gets warmer and warmer and warmer. And I'm making a mess of this picture. Another interesting thing about light is that different wavelengths behave differently in the atmosphere. And this also has implications for greenhouses. You may or may not have heard before, someone might say, why is the sky blue? Well, the sky's blue because shorter wavelengths like blue will scatter. When they hit dust and particles in the atmosphere, they collide and they bounce off in other directions, right? And blue does this more than longer wavelengths. So as the sunlight, which is coming from space, is shooting through our atmosphere, the blue light ends up bouncing off particles and coming to your eyes, which makes the sky look blue. And the rest of the color, the rest of the light just keeps passing on straight through the atmosphere. The flip side is longer wavelengths, they don't scatter much, but they bend more easily. And the idea is that when the sun goes down, you might say, well, why does the sky get orange and red? Well, that's because blue light doesn't bend very well and it scatters. So as the sun goes down, it's passing through more of the atmosphere, which means more of the blue light is scattered. And you're at the end of the train when you're at a sunset. You're the end of the road. So a lot of the blue is scattered and you're left with the reds and oranges and yellows. Plus, as the sun goes down, the longer wavelengths like red can actually bend around the curve of the earth like a lens effect. And that's why the sunset gets redder and redder as the sun gets further and further down. Now, what does this mean for a greenhouse? We'll discuss this on a number of occasions throughout the second year, but obviously as you get wavelengths longer, we go from blue to red, and eventually we get to what we call far red. And far red has a lot of interesting physiological responses on plants. And in the ornamental world, as the sun sets and as the sun rises, those early flashes of far red light bend around the atmosphere and hit our crop. And for crops that are particularly sensitive to stretch, it's important that we block the light in the morning and evening so that our crop doesn't get a big dose of far red light and then stretch through the night. So we often use our energy curtain or blackout at the end of the day, depending on the crop, so that it won't stretch. Just a little tidbit for you there. Another aspect about light that is important for greenhouses is, okay, so as the light comes from the sky and hits our greenhouse, what happens? So when light hits a different density of a surface, so we're going from air to glass, the light, remember, light has both wave and particle properties. There is a little bit of a, think of it almost like a shock wave, like a backwards reflection. A small percentage doesn't get through the glass and is bounced back in the direction it came. And then the rest goes through, right? So let's say we lost 5% to reflection and 95% passes into the glass. Okay, wow, I'm getting better at this. But look what happens. Now the light is exiting the glass and going into a different medium. It could be air, like the top, or it could be a water droplet, so a condensation droplet. Whether it doesn't matter if it's water or if it's air, still another bit will reflect back and you lose another small percentage of the light. So what I'm trying to say is no matter what covering you put on your greenhouse, you'll never get 100% of the light passing through. Glass is obviously the clearest and the best, but even glass does not let 100% of the light through. Now there is a lot of research going into putting coated glass, so glass that has a thin coating on it, which tries to minimize reflection, which means you get 98% passing through. And sometimes they coat both sides and then you have 99%, which, I mean, you have to be really obsessed and have lots of money to spend on these fancy coatings. You've probably seen coatings before. If you've ever looked at the lens of a camera, if you look on an angle, it has a purplish color to it. That's the coating. That's an anti-reflection coating. That means more light will go in the lens, which makes your camera more sensitive in low light situations. Now, let's go back to condensation droplets. Condensation droplets actually have not only another reflection, they have a third reflection as the light leaves the droplet. And so condensation actually cuts down on light transmission significantly. That's why we spend a lot of money and time trying to prevent condensation forming on our glass. Or if it does, we want it to sheet flat, not form droplets, because they will scatter the light and we end up with less light on our crop. Now, sometimes scattered light is desirable. Again, looking at light properties, typically clear glass, if you shine light through, it passes straight through in the exact same path, not how I drew there, but that it entered, it exits the same. That way, when you look through glass, like in this lower picture, you can see the image behind very clearly. Those squares are easy to see because it's clear, right? If you have a frosted glass, or what we call diffuse glass, when you look through it, everything looks a little smoky and unclear. Because as the light passes into the glass, it interacts with this surface and it bends the light in different directions, so it's not entirely clear what's on the other side. Now, there is a lot of interest in diffuse glass in greenhouses, depending on your climate, because if you have diffuse glass, you get less shadow, which means you get softer light, which means light can penetrate into your crop better and you get more efficient use of sunlight. Now in this picture, on the left is regular clear glass, and on the right is diffuse glass. And what you should look at is underneath the bench, look at the shadows. And that is where you can really see a stark difference. So in the clear glass, the shadows are dark, like dark shadows. And in the diffuse glass, they're kind of vague recollection of a shadow. So when you have tall crops like vegetables, where sunlight has to percolate down through all the leaves, diffuse glass actually has more efficient delivery of light to the lower leaves. And so the entire plant is more efficient photosynthetically, as opposed to just the top of the plant that gets the lion's share of the light when you have clear glass, as in on this side. So a diffuse glass is super helpful. This is another picture also showing how clouds can provide diffuse light. So you get less shadows in a cloudy environment. So you don't necessarily, if you have a greenhouse where there's a lot of cloudy weather, say a coastal region, then you don't need to waste money on diffuse glass. But if you have a greenhouse that's in an sunny area, then diffuse glass might be a good investment. I already talked about refraction and stretch. This is just reminding you what it would look like. This is just a little Arabidopsis plant with a little research paper showing how far red light can cause stretch. So yeah, as the sun sets, we got to watch for that far red light that can come around the horizon. Okay, let's look at what plants need. So as far as light, we have visible light, and we talked about that at the beginning. Animals we have eyes that are adapted to the sun, and we can see quite well and perceive that light well. And as far as how we see eye, the human eye is most sensitive to green and yellow. So now I know that's hard to conceptualize because you're saying, yeah, but when I see white, it looks white. Yeah, but that's because your brain is interpreting the signal. The fact of the matter is the human eye is very sensitive to green and yellow. Okay? Where plants have developed their sensitivities to other parts of the spectrum, what chlorophyll sees. And they're trying to make most use of energy in the light. So this graph is showing the peak sensitivity of a human eye. Okay, so you can see definitely in the green-yellow spectrum is where we perceive sunlight. Whereas a plant, the lion's share of its sensitivity is in the blue and in the red, right? But, and I have to emphasize this, if you look at this graph, it still sees other spectrums. This is where some of the LED companies get a little confusing because, they'll say, oh, high efficiency, blah, blah, blah. True, the plant does see red and see blue and UV, but it does make use of the spectrum in the middle. And and to be fair, if you think about it, the plant evolved on the planet with the sun as it is. So why would it just use only two narrow colors and ignore the rest? Obviously, it's going to make do with it what it can. We'll talk a little more about that as we get into the course. But again, so what humans see, what plants see, we call this PAR, photosynthetic active radiation. There's another slide coming up with that, so don't panic. How we measure it, that is going to be my lesson for next week primarily, but let's look at a little bit. There's different terms, lux, lumens, and foot candles, and none of these particular terms are relevant to plants. Okay, it's really important to understand that because on Amazon they sell light meters, hydroponic stores sell light meters, and they're often inexpensive ones, and they measure the wrong spectrum. So anything that's measuring lux, lumens, or foot candles is not measuring the spectrum that plants see. Those units are measuring the human eye response. Okay, so that is really not useful. That's like missing a huge amount of light that the plants could see. So you want to buy a proper meter. You want something that's sensitive to what plants can see. And we call those a PAR meter or quantum meter. Let's talk about the quality of light briefly. There's some terms that are out there, but they're mostly used for household lighting, and that's Kelvin. The color of the light, sometimes it's referred to the color, right? So when you're buying new bulbs for your house, you can have 28K or 5000K. The lower the number, the warmer, the more red the spectrum. So 2800 Kelvin, you've got a light that's heavy on the red side. So that's going to be like a nice warm bulb. And then when you've got a light that is heavier to the blue side, this is going to look like you're in your dentist's office, right? Blue, bright light, harsh on the eyes maybe, but color accurate, right? So they can see very clearly what's going on. Here's another graph showing how the K increases with blue content, right? So the more blue the light, the higher the Kelvin. Again, this is really only applicable to residential lighting, not for grow lights. When we look at spectrums for lights in a greenhouse as opposed to bulbs, they have different spectrums, they have different criteria. We're not necessarily looking at blue, we're looking at the overall picture. This is an interesting one I like to show because this is the spectrum output of a high pressure sodium light up here and an LED grow light with your typical sort of blue, red, and far red. And this one even has some other colors in here, which is useful. It's not a bad light. A lot of times I find the companies that sell these things are a bit misleading, particularly Amazon, stuff, unprofessional stuff. First problem with these two graphs is that the peak output, right? The intensity of the highest peak on an HPS light versus the peak output or intensity of the LED light is very different. So let's talk about it in terms of watts. So if we look at the highest peak output for this light here versus this one, and let's say this one is at 100 watts. All right, that's how much power is in that particular spectrum. If I were to plot 100 watts on this graph up here, right? This is terrible. It's easier if I would have to rescale this top graph to match, and it would look like this. And that might be a little bit of an exaggeration, but it's not far off. And what I'm trying to say is that HPS lights produce a lot of light, And let's be honest, this yellow portion, we know plants use it, but not nearly as much as blue and red, right? So for sure, quite a bit is wasted energy, it seems, versus the LED at the bottom, which obviously is targeting sweet spots with the plant's sensitivity. So you might say it's a little more efficient, but technically, if you look at the output, it's still superior in the HPS. Even though we're wasting energy here, it's still superior in the HPS light. And this is where I'll introduce what I spend a lot of time talking to students about as I prepare them for the industry. You'll see that in industry, almost no one has LED lights in commercial facilities. When we get to the greenhouse technical course in the winter, I got a couple of papers where we can look at it to discuss this in detail. But long and short of it is that the way we can measure the efficiency of a light is we put a quantum meter below the light at a fixed distance. So here's your light and it's shining down. We put a sensor here, okay? And we measure exactly how much energy is going into that meter at the spectrum that plants see, right? At the quantum spectrum. And if this is a 1,000-watt HPS, and this will say it's a 1,000-watt equivalent LED, but it only consumes, let's say, 300 or 400 watts typically to be comparable. Right off the bat, you say, well, this uses less electricity. The trouble is, if you look at this unit and this unit, and we create a scaled unit, so the number of units, we'll call them joules or moles coming into that, of par light per watt, then things actually are almost equal between HPS and LED. So this one produces a lot of light. This one produces a fair amount of light, but 400 watts versus 1,000 watts. Apples to apples, they produce exactly the same amount of light that the plant sees. Now, where things get a little funky, and this is why mainly industry uses HPS, is that technically all this spectrum in the middle that we talked about as being wasted, plus the spectrum down here, this light is not actually wasted. It produces heat. And if you've ever grown plants in a tent, you know there's a lot of heat. And that heat is not lost. In the winter, that heat heats the greenhouse. Most commercial greenhouses, when they turn on the HPS lights, they can turn off their heat. When if you turn on your LED lights, you don't get much heat, which means you still have to run your boilers. So now, from an energy perspective, our LED lights are costing us more money. So we'll get into the facts a little more in the winter, but I just want to alert you to this sort of concept. And if you're ever looking at greenhouses and wondering why do they run HPS lights instead of LED, well, because technically they're running a business. They're not running an opinion website or anything like that. They're trying to make decisions that are going to make the most use of their money. And traditionally, HPS lights have been the case. And also, another sort of knock against against LED lights is that they often advertise them as have 20,000 hours of lifespan. But the reality is HPS lights are super proven, super reliable. Commercial HPS lights often run without any need for service for 5 to 10 years. Technically, you could probably run them for a long time, but the bulb eventually starts to lower its output, and it makes sense to put a new bulb in. So let's say 10 years solid, you're good. LEDs, what's confusing about LEDs is when they talk about having a 20,000 or 20-year or 20,000 hour lifespan, what they're talking about, if you get into the nitty-gritties, is the red LED elements. Red LED elements are the most efficient and are driven with the least amount of electricity. So they don't get as hot and they last a very, very, very long time. But blue and UV LED elements are driven very hard, and most of the industry that has tried LED lights is finding that after a couple of years, all the blue elements are actually starting to burn out. And you wouldn't notice it unless you put a spectrometer underneath and notice that your blue spectrum was actually diminishing, if not completely gone. And that's bad news because now your plants are going to be impacted big time. So long-term longevity of LED lights is still up in the air. Again, here's your PAR blue up into the red spectrum that plants use. We call this photosynthetically active radiation. That's what PAR is. So that's the spectrum that plants use. And we measure it so that we have an idea of how much actual convertible light, the energy the plants are receiving. The units, as we get into some of the units, are actually reminiscent of your fertilizer lesson in root zone. And they are moles, because remember I said light is a combination of waves and particles. So if we treat photons like a particle, and obviously there's a lot of them coming from a bulb, we count them in units of moles, just like we would potassium and nitrogen. So if we're measuring a small amount of light, we measure micromoles. So typically we use instantaneous short measurements of micromoles per square meter per second. And that's how we measure PAR. This is what a PAR meter looks like. It's got a sensor and a wire. It's important that that sensor is level and not under any shade. So it's often on a wire you can set down on the table and walk away. And then you'll see this particular image here is showing 441 micromoles. So that's the amount of PAR light that's available in that particular spot. So we're going to go more into this next week, so I don't want to delve into it too much. And then I hope to bring some quantum meters down to our root zone lab so we can play with those in addition to working in the crops. I'm going to try to use that time to get some hands-on for some of the other courses. I hope you don't mind that. That's it. That's it for this week with the environment class. Let me know if you are lost or have any questions. Take care.